So 3.3 is on two topics, so linearization and L'Hopitals rule. They're pretty small in the grand scheme of AP Calculus. Important, but just not super important, like a tiny bit important. So we do need to go over them, but they're and I think you'll find them pretty easy. So let's go ahead and get started. The one thing, and I don't know how much we actually talked about this, but with derivatives, all differentiable curves are locally linear. So what that means is if you were to zoom in on a point, so for instance, take a graph that's not differentiable, and I'm going to give the example of the absolute value of x. If I were to zoom in on this corner right here and zoom in and zoom in and zoom in and zoom in, it would not change the shape. It will always have a corner there because the derivative from the left does not equal the derivative from the right. The derivative from the left is -1. The derivative from the right of 0 is +1. And that will always be the case. We know that a derivative exists if the left hand and the right hand derivative are both the same. So any other curve, like let's take one that we know is differentiable, like a y = x² graph, if you were to zoom in on this point, even a couple of times, basically what you would get is you would get a straight line. This point right here would turn into, if you zoomed in, a straight line, meaning that it is locally linear, meaning the slope from the left will equal the slope from the right. And that is unlike your absolute value of x graph over here, which will always have that vertical line there. So now, knowing that, what we do is we have this process called linearization. And linearization is a way to approximate. So what we do is we are going to take and we are going to construct a tangent line using our equation y - y1 = m times x minus x1. So that's our first step, is we create the equation of a tangent line. And then what we do is we pick another point, let's say a point that's here on the graph. So it's not on the tangent line, it's on your original curve. And maybe it's not a nice number. So if we're talking about the square root of x, to approximate, I might use, let's see here, the point x = 1, right? Because I know that 1 squared is 1, something like that. Now what I'm going to do is create the line for x = 1, just like normal. So you plug a 1 in for your x1 and you plug a 1 in for y1 because, well, we all know that 1 squared is 1. You figure out your slope of x², plug 1 into that, blah, blah, blah. Now what you're going to do is you're going to pick a point that's not so nice. So let's say, and we call this usually A, but I don't know, just pick another number, 1.1. And then we're going to use our tangent line at 1 to approximate what our value is at 1.1. So yes, that puts the estimation point is on the line, but you're going to use that to approximate the real point that's on the curve, but maybe it's just not so nice to work with. Okay, and then they're going to ask you things like, is the point an underestimate or an overestimate? And a lot of times we'll just sketch a line to see what that is, or we'll know about its concavity. And I know we haven't talked about concavity yet, but eventually we will. Okay, so let's just do a quick example. Find the linearization of the function f of x = the square root of x at x = 9. So there's a perfect example. Then we're going to use a linearization to approximate f of 8. So first off, ignore this. So step 1, ignore. You're going to ignore the not so nice number, and we're just going to work with this information right here. So after I ignore that f of 8, I'm just going to write the tangent line approximation, the tangent line equation given this information right here. So I'm going to start with my y - y1 = m times x minus x1. Now I'm at x = 9. Okay, now I do need to know my slope and I need to know my y value. So y is super easy because if you just plug that in, the square root of 9 is equal to 3. So I have y minus 3 equals. Now to find my slope, slope means derivative. So I'm going to do a little scratch work up here. So y equals x to the 1/2 power. So you guys learned that many times throughout your high school career that the square root of x is the same as x to the 1/2. So therefore y prime, bring the exponent down, so 1/2 x to the negative 1/2 power. And I got that by using my power rule there. Okay, so now I want to do y prime at 9, which is 1/2 x to the negative, not x, sorry, 9. 9 to the negative 1/2 power. Okay, 9 to the negative 1/2 is a third because the square root of 9 is 3. Then it's a negative exponent, so it gets shoved to the bottom. So this is really a half times a third, which is equal to a sixth, which means my slope there is a sixth. Okay, now we've done nothing new at this point. At this point, everything is old. We used a tangent line to find we used the derivative to find the equation of the tangent line. The last thing that I want to do is just solve this for y. So y equals 1/6 x minus 9 plus 3. Okay, now you should also note that this can often be denoted by L of x because that's the linearization. Okay, now what we need to do is we are going to approximate f of 8, which is really like saying approximate L of 8. Notice 8 is very close to 9. 1/6 8 minus 9 plus 3. And that will be equal to 8 minus 9 is negative 1. Negative 1 times a sixth is negative 1/6 plus 3, which is equal to what? 2 5/6. Which is equal to 12 17/6. Lots of different ways to write that answer. You could get the decimal approximation from there. Okay, now one quick thing just to know, if I was to sketch this graph, the square root of x looks like this. Okay, at x equals 9, I would put my point and I would draw my curve in. And now if I'm estimating at 8, so it's going to be kind of hard to see here, but 8, something like that. I'm hoping you can see that the approximation, this value right here, so L of 8 will be an over approximation. And that's because the tangent line is above the curve there. So you'll get the value that you estimate is higher than the actual value is. Okay, so step 1, ignore what you're approximating. Bring that in at the very end. Write the equation of a tangent line. When you have the equation of a tangent line, then plug in the value to approximate. Okay, so here's one other quick example. So we've got f of 2 equals negative 6. The slope at any point is given by f of x over y squared. Write the equation of the line tangent and then use it to approximate y, f of 1.8. So step 1, remember, step 1, ignore this. So ignore. And just start with y minus y1 equals m times x minus x1. Okay, now they gave me everything here except for the slope, but it'll be really easy to find. So y minus a negative 6 equals, let's come back to the slope in just a moment, x minus 2. Now to find my slope, they said the slope at any point is given by this. So that means I just need to plug in my values. So I'm going to have 5 times 2 all over negative 6 squared, which gets me 10 over 36 to be my slope. Y minus a negative 6 is y plus 6. To get my linearization, which is equal to y, that will be equal to 10/36 x minus 2. And that will be minus 6 because we've got plus a positive 6 over there. So now I want to use that to estimate 1.8. So that will be equal to 10/36. 1.8 minus 2 minus 6. Let's see here. 1.8 minus 2 is 0.2. Is that correct? I hope. 0.2 is 2/10. So I believe I have 1036 times 2/10 minus 6, which gives me 1/18. Is that right? I'm doing a lot of mental math here, but 1/18 minus 6, which would be equal to, I may have got that last one wrong. I might have forgot a negative in there somewhere. Oh, no, I didn't. I was good. So -6 minus an 18th. Well, just figure it out. Just go to a calculator at that point. Okay, L'Hopitals. So linearization. Again, ignore the second number that you're approximating. Write the equation of the tangent line, then put in the point that you're approximating. L'Hopitals. L'Hopitals is one of my favorite rules. And then we're going to go back to limits for a second with here. When you have the limit of f of x over g of x. So we're going to get to examples of this in a moment. The first thing you do with limits is you plug in whatever you're approaching. So like, let's say we've got the limit as x approaches 2 of, I don't know, x squared over x to the 5th, something like that. Okay, so the first thing you always do is you plug 2 in and you see if you have any problems. I don't have any problems here, so I would be fine to say whatever my answer would be. So that would be 1 over 2 to the 3rd, so 1 equals 1/8. Okay, so step 1, you always plug that value in. Now, what happens when you get an indeterminate form? Now, what do I mean by indeterminate form? You get 0 over 0 or infinity over infinity. What we have found is that what you can do is take the derivative of the numerator and the derivative of the denominator. This is not quotient rule, by the way. This goes back to limits. If you plug in that value and you get an indeterminate form, 0 over 0 or infinity over infinity, you can take the derivative of the top and the derivative of the bottom, then plug in the value and see if that gives you what the limit is. Okay, so here's our first example. So step 1, plug 0 in. If we did that, we would get 0 squared over sine of 0, which gives me 0 over 0. That is an indeterminate form. So L'Hopitals rule says you can do that is equal to the limit as x approaches 0 of the derivative of the top over the derivative of the bottom. So the derivative of x squared is 2x divided by the derivative of sine x. Remember, sine goes up through the origin, so it will give me cosine of x. Now plug in the derivative. Remember, you can drop the limit as soon as you plug in the value. So we're going to have 2 times 0 over cosine of 0, which gives me 0 over 1. Cosine of 0 is 1. You can check your unit circle. You can think of the graph, which gives me 0. Okay. And you can check that on a calculator. Super, super easy. So step 1, plug in your value. We have a negative infinity here. So we have 3 times negative infinity minus 2 all over e to the negative infinity squared. And that will give me, on the top, we'd get what? Negative infinity. 3 times negative infinity minus 2 is negative infinity. And then on the bottom, we've got e to the infinity power. Kind of surprised we didn't get an infinity over an infinity. But anyways, indeterminate form, I'm hoping that this would work. Guess I should have checked never seen that before. Because I don't want to give you a wrong answer. Let's do this one in class together. Remind me, and I'll look up how to do that. I just don't want to give it wrong in the video. Okay, let's look at this one really quick. The limit as theta approaches 0. So again, if you plug in sine of 0 over 0, that gives you 0 over 0, which is your indeterminate form. You take the derivative of the top and the derivative of the bottom. The derivative of sine is cosine. The derivative of theta is 1 with respect to theta, of course. You get 1 over 1, and that is equal to 1. This one, if you plug in the infinities, these are positive, so I know that they'll work. But you can look here down here at the rules. You would get the indeterminate forms, infinity over infinity. Take the derivative, you get 6x plus 1 over 10x plus 8. If you plug in infinity, you will again get infinity over infinity, still indeterminate. So we do it again, which gives you 6 over 10, which equals 3/5. Now, by the way, you probably knew that just by looking at this because of our limit rules. We would look at the degrees, and this is a second degree polynomial in the numerator, a second degree polynomial in the denominator. So we would have just divided that out by 3/5 in the beginning, and it comes from L'Hopitals rule. We've actually been doing that for a while. Okay, and this is my last example that I have for you. And again, if you plug in 0, you're going to get the indeterminate form 0 over 0. So you take the derivative. Again, you get 0 over 0. Take the derivative. Again, you get 0 over 0. So you take the derivative, in which case you would get e to the x over 6. E to the 0 is 1, which gives you 1/6 as your answer. So you can look through that work if you need to. Okay, so like I said, we'll go over that one in class. Sorry about that. Other than that, basically all you need to know is when you do step one with any kind of limit, any limit ever, you always plug in what you're approaching first to see what happens. If you ever get that indeterminate form, 0 over 0 or infinity over infinity, take the derivative of the top, the derivative of the bottom, and then plug in the value. And you can do that many times until you get something that you can actually plug in the value and not get the indeterminate form. Okay, so those are your two rules. You've got linearization, write the equation of the tangent line, and then plug in an approximation. And you've got L'Hopitals. Now time to practice.